Hi guys, welcome back to YouTube channel Chemistry Live UGPG. Today we are going to talk about carbonyl compounds lecture 4. So this will be highly beneficial for BSc chemistry students under CBCS syllabus. I have a simple message for you guys. Please think for innovation, be creative, learn everywhere, anytime and help to learn others. So today we are going to talk about Wittig reaction, Beckmann rearrangement, haloform reaction and Baeyer-Villiger oxidation. So this is coming under CC6 paper semester 3 unit 3 carbonyl compounds. So this is the prerequisite knowledge that everyone must have. So usually the reactant is converted to the product with the help of reagents. So how that reactant is converted to the product with the help of reagents, that is the mechanism. So what mechanism tells us? So mechanism shows the movement of double-headed arrow, how bonds are broken and new bonds are formed, leading to formation of product, which may be multi-step or one-step process. So usually the bond is represented by the two dots or a single line. So when this bond is broken heterolytically on this atom, so on which atom it breaks, that gets both the electron with negative charge and other atom gets positive charge. So this is electronically deficient A plus, that is known as electrophile, and X minus with both the electron, that is known as nucleophile. So usually the nucleophile will attack to the electrophile in principle and giving rise to nucleophile electrophile bond. So let's start with Wittig reaction. So what is Wittig reaction? Aldehyde or ketone when treated with alkylidine triphenyl phosphoran, that is called Wittig reagent. So this compound is known as a triphenyl alkylidine triphenyl phosphoran. This is Wittig reagent and it gives alkene. So this reaction is called Wittig reaction. So you react with a ketone and this is the Wittig reagent. So that is this C double bond O will be converted to C double bond CH2 and triphenyl phosphine oxide. So similarly, if you react with cyclohexanone with Wittig reagent, you will end up with C double bond CH2. So how to prepare Wittig reagent? So first you have to start with triphenyl phosphine and you have to react with alkyl halide. So you will end up with this intermediate and this upon reaction with phenyl lithium. So this pH minus will take the proton from methyl. So you will end up with this Wittig reagent, alkylidine triphenyl phosphoran plus lithium bromide plus benzene. So let's talk about how the reactant is converted to the product. So this PS3P double bond CH2. So you can have resonance structure. So CH2 minus, PPS3 plus. This is B10. So this CH2 minus will act as nucleophile. It will attack to carbonyl carbon and C double bond O will break on oxygen. So as a result, you end up with O minus and PPS3 plus. It can form a 4-membered cyclic compound which is unstable and again bond making and bond breaking takes place, giving rise to the product alkene plus triphenyl phosphine oxide. So usually the driving force for formation of alkene is the formation of a phosphorus oxygen bond at the expense of a phosphorus carbon bond. Next is what is Beckmann rearrangement. Acid catalyzed rearrangement of an oxime to an amide is known as Beckmann rearrangement. So usually cyclic oximes give rise to lactams. So if you start with RCOR, it would react with a hydroxylamine. You will end up with oxime and in presence of H2SO4 or H plus, you will end up with amide. This is called Beckmann rearrangement. Similarly, if you start with cyclohexanone and you react with hydroxylamine, you will end up with cyclohexanone oxime. And in presence of H plus, it would give caprolactam, the cyclic amide. So let's talk about the mechanism. So this is the oxime. So oxygen lone pair can act as nucleophile. It will attack H plus. So this becomes OH2 plus. So here the rearrangement takes place. Nitrogen lone pair will attack this R group and CR bond will break on here. And it will kick out this NO bond will break on O plus. So as a result, you end up with this species. This undergo resonance. we end up with a carbocation, and water can act as nucleophile, so it will attack this carbon. It will attack to C plus. So you get this protonated water, and it will lose one proton, giving rise to this enol, and this enol tautomerizes to give rise to amide. So there is a problem for you guys. Please write down the mechanism for caprolactam formation. So if you start with cyclohexanone, react with hydroxylamine, you get cyclohexanone oxime. And in presence of H plus, you get caprolactam. So please write down the mechanism for this one. Next is a haloform reaction or iodoform reaction. So the oxidation of methyl ketones in presence of sodium hypohalide, that is alkaline solution of halogen, to give an acid containing one carbon atom less than the parent ketone and haloform. So this is the methyl ketone CH3COR. So in presence of iodine and sodium hydroxide, you would get the acid which is one carbon atom less than the parent ketone and the iodoform or haloform CHI3. So what is the mechanism? How you convert this methyl ketone into carboxylic acid? So this RCOCH3 we can write like this, and OH minus ion can act as nucleophile. So this OH minus ion will take the proton, and this bond will break on carbon. So once you generate this carbanion, this CH2 minus can again react with iodine. So you get RCOCH2I. So once you get the RCOCH2I, again this would undergo in a similar fashion two-step reaction with OH minus ion and I2, giving rise to RCOCI3. So once you get this product, so OH minus ion again in the reaction medium, it will act as nucleophile. So it will attack this carbonyl carbon, and C double bond O will break on oxygen. So as a result, you end up with this tetrahedral intermediate. So once you get this, so when this O minus will come back, it will kick out CI3 as CI3 minus. So you end up with carboxylic acid plus CI3 minus. Again the proton transfer takes place, giving rise to RCO minus plus CHI3 iodoform. So next is Baeyer-Villiger oxidation. So if you start with the ketone and you react with pore acid, you will end up with ester. Similarly, cyclohexanone react with pore acid, you will get lactone. This is cyclic ester. So now question arises, what is pore acid? So the pore acid formula is RCO3H. This is the structure R C double bond O OOH. So now question arises how to prepare this pore acid. So you have to start with the carboxylic acid and you react that with hydrogen peroxide, giving rise to RCO3H plus water. So these pore acids are 1000 times weaker than the parent carboxylic acids. And the oxidizing power of these pore acids follow this order: CF3CO3H greater than CH3CO3H greater than hydrogen peroxide. And how to prepare this hydrogen peroxide? So you have to start with ammonium peroxide disulfate and react that with water, giving rise to hydrogen peroxide. So if you start with cyclohexanone and you give pore acid, you will get lactone. So this oxygen has cyclohexanone. Oxygen has lone pair of electron that can act as nucleophile. It will attack to the H plus of hydrogen of the pore acid. So this OH bond will break on oxygen. So you will end up with this protonated hydroxyl. Again RCO3 minus, so it can act as nucleophile. So RCO3 minus will attack this carbonyl carbon and this double bond will break on O plus. So as a result, you end up with this species intermediate. So when this bond will come here the sigma bond migrates. So this C sigma bond migrate to the oxygen, and this O bond will break on oxygen atom. So as a result, you will end up with lactone plus carboxylic acid. So please subscribe to our channel Chemistry Live UGPG. So this is also available in the website www.chemistryliveugpg.com. So for class 11th and 12th students, this is the channel Foundation Chemistry AB. This is also available in the website www.foundationchemistryab.com. So this is a simple step towards e-learning, making life better. Thank you all for learning.